Today we'll discuss the properties of LTI systems in terms of impulse response. Impulse response is presented as h of n. What is impulse response? It is a response of a system due to unit impulse function, that is del of n. The properties are memoryless, causal, stable, invertible and deconvolution. Now first I'll go for the what is memoryless. Any LTI system is said to be memoryless if its output depends only on the present values of the input. When you want to talk in terms of this, in terms of impulse response, any LTI system is said to be memoryless if its impulse response h of n, is equal to 0 when n is not equal to 0. Okay. Any system is said to be memoryless if its impulse response h of n is equal to 0 when n is not equal to 0. This is in case of discrete time LTI system. Similarly, in case of continuous time LTI system, it is h of t is equal to 0 for t is not equal to 0. This is the condition to say that it is in memory or memoryless. If this condition is satisfied, we can say that it is memoryless. Otherwise, if the impulse response exists outside this range, then we can say it is a memory system. Okay. Next, what is causal? Causal. Any system is said to be causal if its output depends on present and or past input values. When you want to say the that is causality of an LTI system in terms of impulse response, okay, system is said to be causal if its impulse response h of n is equal to 0 for n is less than 0. That means to say it is a causal, thus impulse response of the LTI system should be only at the right hand side. Okay? That means if its value is 0 when n is less than 0, then we can say that that LTI system is said to be causal. Similarly, in case of discrete time system, h of t is equal to 0 for t is less than 0. Next, we'll talk about its stability. Stability. Any system is said to be stable if it gives an bounded output for a bounded input. If input is bounded, if output is also bounded, then we'll call it as a system is bounded. That is called BBO stable. That is bounded input, bounded output. Bounded input and bounded output. Now, in terms of impulse response, how to say that system is stable or unstable? Now we know that is output of an LTI system is given by y of t is equal to x of t, that is linearly convolved with h of t. If input is considered, if input is bounded, let us consider the input has that is less than or equal to some value bx, that is less than infinity. Here input is bounded. Similarly, we can take in case of continuous also. Here input is bounded. Now let us evaluate its output in terms of impulse response. First, I'll consider the discrete time LTI system. Consider discrete time LTI system. Consider a discrete time LTI system, that is, we know that y of n is equal to, take its absolute value, y of n is equal to x of n, that is linearly convolved with h of n. Using commutative property, I can write that x of n is linearly convolved h of n can be written as h of n, that is linearly convolved with x of n. Then we know the convolution sum formula, that is, summation of k tends from minus infinity to plus infinity h of k into x of n minus k, that is y of n equals to, summation is outside, summation of k tends from minus in plus infinity x of k h of k and x of n minus k. Okay, since x of n is a bounded input, x of n is less than or equal to bx, that is less than infinity, then we can write that x of n minus k also less than or equal to bx, that is less than infinity. That means this is a constant here, that we can take it outside, that is we can write that y of n is less than or equal to x of n minus k, summation of k tends from minus infinity to plus infinity modulus of h of k bx. I take bx outside, that is less than or equal to bx, summation of k tends from minus infinity to plus infinity, it is the absolute value of h of k. This is the output. From this we can conclude that y of n is finite, it gives the bounded output. If this is summation of k tends from minus infinity to plus infinity of magnitude of h of k is absolutely summable. That means this should be less than infinity. This is finite. If this is also finite, then answer output is also finite, that is bounded. That is summation of k tends from minus infinity to plus infinity magnitude of h of k, summation of k tends to minus and plus infinity, magnitude of h of k should be less than infinity. That means we can say that any discrete time LTI system is stable if its impulse response is absolutely summable. This is for all values of n. So n. Okay, that means finally you can say that discrete time LTI system, discrete time LTI system is stable only if impulse response h of n is absolutely summable. Only if its impulse response h of n is absolutely summable. Okay, that means condition to check for the stability of a discrete time LTI system is summation of k tends from minus infinity to plus infinity, magnitude of h of k should be less than infinity. Similarly, let us consider the continuous time LTI system. That is, consider continuous time LTI system if input x of t is bounded, x of t is less than or equal to bx, that is less than infinity, output y of t of any continuous time LTI system is given by x of t is, that is linearly convolved with h of t. This can also be written as using commutative property h of t, that is linearly convolved with x of t. Using the convolution integral formula, we can write that integration of minus infinity to plus infinity h of tau x of t minus tau into d tau. If x of t is less than equal to bx, that is less than infinity, then x of t minus tau, that is also less than equal to bx, that is less than infinity, then we can write that y of t is equal to integral of minus infinity to plus infinity h of tau, that is bx to d tau. X is a constant that we take it outside, integration of minus and plus infinity magnitude of h of tau into d tau. Okay. To say it is stable, this must be less than or equal to infinity, that is y of t less than or equal to bx less integral of minus infinity plus infinity integral of absolute integral of h of tau, that must be less than infinity. From this I can say that system is stable if integral of minus infinity to plus infinity h of tau into d tau is less than infinity. That means any continuous time system is said to be stable in terms of its impulse response if its impulse response is absolutely integrable. If its impulse response is absolutely integrable. Okay. Continuous time system is stable if its impulse response h of t is absolutely integrable. Okay. Next, we go for the next property. Last one is invertible and deconvolution. Invertible and deconvolution. What is invertible? Any system is said to be invertible if we are able to recover its input from the output. If we are able to recover the system input from the output. For example, if we take in system 1 here, input is x of t, output of system 1 is y of t. Due to the another system 2, if we are able to get back the original input x of t, then we'll call it as it's an invertible system. Then we'll call it as it is an invertible. That means what is an invertible? Any system is said to be invertible if the input is recovered from its output signal. How you can recover this? For example, if you take an LTI system, its impulse response is h of t, input is x of t, and what is its output? output is equal to here, output is equal to x of t is linearly convolved with h of t. Output is y of t is equal to x of t is linearly convolved with h of t. From this output, I should get back the original input signal x of t. That means this is system 1. Another system 2 is the, I should use the inverse of this system. That is, what I will do here is I will take the, this is system 1. Its input is x of t. I'll give to the another system, that is inverse system. Inverse of this system, that will correct as h inverse of t. Then this is the output y of t. Its output will get it as an x of t. How do you get this? When you see this, x of t is linearly convolved with h of t. That is linearly convolved with h inverse of t. That is, x of t is linearly convolved with h of t. Result of this is linearly convolved with the inverse system. We'll call this as an inverse system. Inverse system, h inverse of t. Using associative property, I can write that x of t is linearly convolved with h of t, that is linearly convolved with h inverse of t. Okay. When h of t is linearly convolved with h inverse of t, we'll get impulse function del of t. When x of t is linearly convolved with the impulse function del of t, output is x of t. We'll get back its original signal. This will call it as an deconvolution. This will call it as an, this process will call it as an process of recovering the input from the inverse system. We call it as an deconvolution. Process of recovering the input x of t from the system output, we'll call it as deconvolution. Deconvolution is the process of recovering the input x of t from the output y of t is called deconvolution. How we are recovering it, I have shown this in this. Okay. Now I'll take one example here. Let us take one example. Example is, let x of n is equal to 2 to the power of n into u of n. Let us check it is memoryless, causal or stable. X of n is equal to 2 to the power of n into u of n minus 1. U of n minus 1 is a signal which exists from 1 to infinity. When you draw the signal, x of n, it looks like this. At n is equal to 1, its value is 2 to the power of 1. N is equal to 2. When n is 0, it will become u of minus 1. U of minus 1 value is 0. It goes like this. This this is n, this is 0, this is 1, 2, 3, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. This goes like this. This is the x of n. This signal exists from 1 to infinity. Now, is it memory or memoryless? What is the condition for memoryless? H of n, sorry, this is h of n. H of n is equal to 2 to the power of n into u of n minus 1. Here h of n is there from 1 to infinity. To say it is memoryless, h of n should be equal to 0 when n is not equal to 0. But this condition is not satisfying here. Hence it is memoryless. Okay. To say it is memoryless, hence it is a memory system. Hence it is a memory system. What is the condition for memoryless? H of n must be equal to 0 when n is not equal to 0. Since that condition is not satisfying, it is a memory system. Next, causality. To say it is a causal, condition is h of n is equal to 0 when n is less than 0. This condition is satisfying because signal does not exist when n is less than 0. Hence it is a causal system. Hence it is a causal system. Then to talk about stability, what is stability here? Stability is, we know that is absolute sum of the impulse response of this system is absolutely summable. That is summation of k tends from minus infinity to plus infinity. H of k must be less than infinity. Here this exists from 1 to infinity. That is summation of k tends from 1 to infinity. H of k, that is equal to, when k is 1, h of 1 value is, that is 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3. It goes like this, becomes infinity. That means it is unbounded. It is not bounded, it is unbounded system. And system is unstable. System is unstable. Okay. Here impulse response is h of n is equal to h of n is equal to 2 to the power of n into u of n minus 1. To say it is memoryless, condition is h of n must be equal to 0 when n is not equal to 0. Since that condition is not satisfying here because it exists from 1 to infinity, hence it is a memory system. And to say it is a causal or non-causal, it's said to be causal if h of n is equal to 0 when for n is less than 0. That means when n is less than 0, signal does not exist, condition is satisfying, and so I can say that it is a causal system. To say it is stable, that is impulse response must be absolutely summable. That is when summation of k tends from minus infinity plus infinity, h of k must be less than infinity. Since it exists from 1 to infinity, take 1 to infinity h of k. When k is 1, it will be 2 to the power of 1. When k is 2, 2 to the power of 2. When k is 3, 2 to the power, it goes like this. And add up, it tends to the infinity. Hence, it is an unstable system. Okay. Thank you. This completes this topic.